Hello class, welcome back. We're going to talk about 1.5, which is the topic infinite limits. Basically what we're going to have is that we're going to have some limits of a function that are approaching infinite value. So the objectives are to determine infinite limits from the left and from the right, and find and sketch the vertical asymptotes of the graph of a function. So we'll begin by defining what's an infinite limit. So if you guys notice in this example, we see a graph being broken into two parts, right? So we see the left side and the right side. Now, if you notice that as x is approaching, so if this is the function, and as we are approaching the value of 2, which is right here, notice that this is keeping going up by 2's. So if x is approaching 2, the value of the function, right, if you guys notice, as x approaches 2, the value of the function is the black line right here, and it's going down, it's lower, and it's going decreasing. So as I get closer here, the function is decreasing, and I get closer, the value of the function is decreasing. So the closer I get to 2, the value of the function decreases more and more and more. And we can kind of see that in the picture, in the table as well. If you guys notice, as x is approaching the value of 2, which is the top row, 1.5, 1.9, 1.99, and so on, the value of the function becomes -6, -30, -300, -3000. So it seems like it's getting decreasing by a lot, right? So it's decreasing without bound. Now it's gonna be confusing for you guys, because when you guys think about decreasing, you automatically think about just decreasing down to the value of 0. But in this case, in mathematics, we can go and decrease to the negative values. The more negative you are, the further you are lower, the more you decrease. Now in this example, that means that this is going to decrease without bound. So it's going to decrease, and so what we're going to do is we're going to sort of describe this sort of value that is decreasing forever without bound as a negative infinity. Now we want to establish that infinity is not an actual number. It's not a real number. It's more like a symbol that represents a number that can never be reached, right? Infinity is a number that you can never reach. You can never say, oh, I can get to infinity. This number is the biggest number I can get. Well, that's not true, because I can always just add another number, and now I have a bigger number, right? So infinity is something that we'll never be able to reach. And the other side here, as x approaches 2 from the right side, notice the value of the function, which is the black line right here. It's increasing. The value of the function is increasing because it's going up. Remember, the value of the function goes up and down. The value of x goes left to right. So the value of the function is increasing as you get closer and closer to 2, right? So you guys see here, and it's going to do the same thing. It's going to approach infinity without, so it's going to increase without bounds, which means it's approaching infinity, right? So we can see that also in the table. As we are approaching 2 from the right side, we have 2.5, 2.1, 2.01, 2.001. As we get closer to 2, the value of the function, which is the second row, is 6, 30, 300, and 3000. So the closer we get, the bigger it gets. So we can see here that we sort of have this describing the two behaviors from both sides. And we are able to say, well, the limit of the function as x approaches 2 from the left side is equal to negative infinity. The limit from function 3 over x minus 2 as x approaches 2 from the right side is positive infinity. Now, let me say this right now, that the limit does not exist in either way. That does not exist. So this is technically does not exist. But what we're going to be doing, instead of saying does not exist, we're going to say something a little more specific, and we're going to say, okay, it does not exist, but we're going to say it's equal to infinity or it's equal to negative infinity. I hope that's kind of clear. It is just we just sort of is already established that infinity it's not a number, so everyone knows that. But we can be just a little more specific to the reader, right? If you're giving this information to someone else, it's just important for us to give that extra information so that it can make the contextual conclusion of what's happening. All right, so here we have the definition of an infinite limit, and pretty much what it's saying is that it's just approaching is increasing without bound or decreasing without bound. Now, it's important for us to remember that the limit of a function as x approaches c, that means it has to come from the left side and the right side. They both have to approach the same number in order for us to actually say something about the limit itself, right? So here we're just discussing the left side and the right side individually, but if you want to know the limit of the function as x approaches c, that means that these two need to be the same, right? They both need to be positive or they both need to be negative. So as you guys can see here in the next picture, the limit of the function as x approaches c, if you notice, as you get c from the left side, the function is approaching infinity. As x approaches c from the right side, is also going to positive infinity. So because they're both going to positive infinity, then you can conclude that the function is approaching infinity as x approaches c. All right, so we still got to be checking the left and the right, right? All right, so here let's talk about some examples. And we notice that the definition can be very complicated using delta and epsilon, but we're just going to stick to the concept, the application itself. So let's look at this example. They want us to just discuss the limit of each function approaching 1 from the left and approaching 1 from the right. So we're just discussing each one individually, left and right. So our question is, given this function, what is the limit of the function as you approach 1 from the left side, and what's the limit of the function as x approaches 1 from the right? I already have the solution here, or the answer, but let's see how are we gonna make that up. So obviously here we have a picture. We can kind of see that as x approaches 1 from the left side, it seems like it's moving that direction up, right? How do we know that we have to move from the left to here? Because remember that we're trying to approach 1, and so you're coming from the left, so that means you're sort of starting from the left side and then just getting closer and closer, moving to that direction. So that tells you how the graph needs to how do you monitor the graph, right? I'm monitoring the graph by looking at what's the behavior of the graph, and it seems like it's increasing, right? And then it's increasing also coming from the right. So now coming from the right, the function, it seems like it's increasing, right? It's increasing because my point is going up. Now let's look at this at the table, right? Because we can assume that we're not going to have a graph all the time. So what I did here is I just plugged in a few numbers. We're approaching 1 from the left side, so I started by putting 0.9, and then I got closer by saying 0.99, and I could have been a little closer by saying 0.999, right? So you guys see how the pattern is. So I plug in 0.9 into the equation, and I end up getting 100. Then I plug in 0.99 and I end up getting 10,000. So that's kind of neat. Okay, I can kind of guess that it's gonna go to infinity now, right? So yeah, so that's what happened. It's just going to infinity. Now from the right side, I plug in a number that is close to 1.1, but then 1.1, and then I try another one, 1.01. That's even closer to 1, right? So I plug in that number into the function. And that got me 100, and then I plug in 1.01 into the function, and I got 10,000. So it seems like it's also increasing without bound, right? And you can try a few more numbers if you don't feel like you haven't seen the pattern yet. So I feel confident that this is gonna go to infinity. So if you notice, they're both going to infinity. Now let's jump into the next one. So we have a function that is negative 1 over x minus 1. Just a little bit different than the last one, and we're going to do the same thing. We're trying to figure out what's the limit of the function coming from the left and what's the limit of the function coming from the right. So let's try that. So let's plug in 0.99, that's coming from the left, and if I plug in 0.9 into the function, I get 10 overall. If I plug in 0.99, I get 100 overall. So it seems like coming from the left is increasing. It's increasing pretty rapidly. So it's going to be going to infinity. Again, you can try a few more if you don't see the pattern there. And then I tried numbers from the right side, coming from the right side, so 1.1, 1.01, and I end up getting negative 10 and negative 100. So it seems like it's the same numbers as the other side, but these are opposite sides, so it's actually negative. So it seems like this is going to be going to negative infinity, right? In all cases, the limit does not exist. The limit does not exist. Let's be clear. This is technically does not exist, but we can say something extra, right? We can say that is approaching infinity, right? That's saying the same thing, but we're being a little more specific. All right. All right. So, okay. So moving on. So how do we use this? So this is very convenient for us to use when we're talking about or describing the characteristics of a graph. And this is something you guys have seen in pre-calc in college algebra, that when this happens, when we actually have this limit approaching infinity or negative infinity, what we end up actually having is something what we are familiar with is called a vertical asymptote. So here, in the first example, we have 1 over 2 times x plus 1. We end up having that as you come from the left side to in approach negative 1, you end up going decreasing, decreasing. So you end up going to negative infinity. Coming from the right side, you end up actually going to positive infinity. So here we have established that there is a vertical asymptote. Similar with the other one, we see here that we are also going to get an asymptote, and we end up getting 2 asymptotes here. And we can kind of do the table, and we can observe that this is what's going to happen, right? We're going to, as we approach negative 1, we're going to be going to positive infinity from the left side. As you approach negative 1 from the right side, you're going to go to negative infinity. As you approach 1 from the left side, you're going to go to negative infinity. And as you approach 1 from the right side, you're going to go to positive infinity. Now, it would be kind of tedious for us to do all these tables all the time. So you guys already know how to find these vertical asymptotes, right? So we're going to be using sort of the same strategy, same concept. So do you guys remember how we did that in pre-calc? We only had to do this, right? We just had to look at the bottom part, and then make the conclusion, right? So it was something with the bottom, right? So let's look at the definition. If f of x approaches infinity or negative infinity as x approaches c from the right or the left, then the line x equals c is a vertical asymptote to the graph. But we also generalize this concept by using some algebra. We said that this is going to happen, that each function is that each of the function is a quotient, and that it has a vertical asymptote when the number in the denominator is 0 and the numerator is not 0. So if you have that case where you have a quotient and you happen to know when the denominator is 0, and then in that same value of x the numerator is not 0, then that means it's a vertical asymptote. So let me just go over this theorem real quick. Just let's read it real quick. So let f and g be continuous on an open interval containing c if f of c is not equal to 0, which is the numerator, but g of c is equal to 0, and there exists an open interval containing c such that g of x is not equal to 0 for all x not equal to c in the interval, and then the graph h of x has a vertical asymptote. So it does seem like more complicated than it sounds. It's something you guys have done before, so this is supposed to be sort of kind of like a quick review, but we were able to sort of connect it to this limit now. So let me just go over this first problem. Let's find the vertical asymptotes to the graph of these functions, right? So we're looking at the first one. So what we're going to do is we're going to look at the bottom, and we're going to see, okay, when would the bottom equal 0? Can we guess that? Yes, right? So the bottom will equal 0 when x is negative 1, right? Now, at negative 1, would that make, when you plug in negative 1 to this function, would that make the numerator be 0? Not in this case. So the denominator of f of x is 0 when x equals negative 1, but the numerator is not 0. So by theorem 1.14, we can conclude that x equals negative 1 is a vertical asymptote. So that would look like this. So just right there. So this dashed line is the vertical asymptote. Now, does it matter that one decreases and the other increases? No, it doesn't really matter, right? And when doing vertical asymptote, you just know there is a dashed line there that cannot be crossed, right? Just a quick reminder from pre-calc. So let's look at the next one here. Function b. Function b, it's another quotient, right? So it's nice. Once we have a quotient, we can kind of see what we have. So first of all, recognize when would the denominator be 0. So you guys notice I always jump into the denominator. That's my main focus. So I jumped into the denominator, and I want to know when would the denominator be equal to 0. So I sort of solve for the bottom when this is equal to 0. So, but it's better if you actually factor it. So this is one of the occasions where you factoring is such a nice skill to have. So I would automatically factor the bottom and also the numerator. So, but in this case, that's not factorable. So I have this, and can I guess when the denominator will be 0? Yes, the denominator will be 0 whenever this factor is 0 and whenever this factor is 0, which happens at x equals 1 or x equals negative 1. Now, when x equals 1 or negative 1, the denominator of fx is 0. But notice that when x equals 1, the numerator would not be 0. In fact, if you plug in 1 there, that would be 1 squared plus 1, that would be 2. Same thing if you plug in negative 1 there, the negative 1 will be squared, which becomes a positive, which becomes 1, and you add it to 1, that becomes also 2. So denominator is 0 for 1 and negative 1, but not for the numerator. So here we have the line that says when x equals 1 or x equals negative 1, the denominator of x is 0, but the numerator is not 0. So by the theorem 1.14, we can conclude that x equals 1 and x equals negative 1 are vertical asymptotes of the function, and you guys can kind of see that in the next picture. So you see those vertical asymptotes. Right now we're not worried about too much about the graphing part. We're actually gonna have a whole chapter of that, of graphing, so please keep this in mind as we're moving forward. And if you have to go back and review some of your notes from college algebra, please do so. But this is mainly gonna give you a good review. All right, so the next one, we have the cotangent of x. Now, if we see cotangent of x and you're trying to figure out what's the vertical asymptote for that, remember your motivation is to have it as a rational function. So automatically you should be thinking, okay, how can I rewrite cotangent in a form of a fraction? Well, tangent happens to be sine over cosine. Cotangent happens to be the reciprocal of tangent. So instead of having sine over cosine, now we have cosine over sine. So you should be familiar with these properties, right? But anyways, I wrote it as a rational function. So when I have a vertical asymptote, whenever the denominator is 0, right, and the numerator is not. So I put this note here. We conclude that cotangent of x has a vertical asymptote when sine of x is 0 and cosine of x is not equal to 0. And if you guys see the unit circle, this is going to happen when your angle, when x is the angle 0, when is the angle 180, when is 360, and so on and so on and so on. So what I did here is, it seems like all we had to do is going to be a multiple of pi. So you're just going by pi. So I decided to rewrite it here as a it will be every single time the angle is a multiple of pi, and so that will be the best way to do it. If you're unfamiliar with that way, remember that you have to go back and review some of your tricks. Obviously here k is any integer. It could be -1, could be -2, it could be 0, it could be 1, it could be 2. So we are sort of defining all those cases by saying k is any of those integers. And you guys can see that we have multiple asymptotes here. You can see how those are those dashed lines, right? So here we have many asymptotes. All right, so it's important for us to be familiar with all these definitions of asymptotes. So please make sure you guys review that. Some of the properties that we want to keep in mind are kind of important for us, is sort of extending like an exception of the theorem that we have seen before. Remember that we said that a limit can only be broken down from a summation, from a product, from a division, only if both limits existed. Well, in this case, we're sort of giving an exception for that. So that means that if the limit of the function is infinity and the limit of the other function goes to a real number, then what we're saying is that the limit of infinity will overpower the sum of those two, making it go to infinity. So it kind of makes sense, right? If something is big, if one part of the function is becoming very, very big, and the other part is becoming very, very is just a constant, it's like adding. So you don't want to do this. I mean, this is not a formal thing, but you can think about it this way. It's like adding infinity to a constant, right? It's like adding infinity plus 3. Would that make the difference of infinity? No, right? Infinity is still good infinity. It's a number without bound, right? I mean, it's not a number, it's actually just an expression, but it's something that doesn't have a bound. 3 is going to be insignificant to infinity, right? Or if you subtract it, right? If you subtract 3 from infinity, that's still going to be infinity. What about when you have infinity times a number, right? If you have infinity times 3, let's say, would that make a difference? Like if you multiply infinity times 3? No, right? You're still going to have infinity. Now, if that coefficient, right, 3 becomes negative 3 and you have infinity times negative 3, what's going to happen is going to flip the value of the infinity, making it negative infinity. So that kind of makes sense. What about when you have a quotient? If you have a quotient and you have a real number above like 3, but then you have infinity on the bottom part, then you have sort of dividing 3 by a huge number, right? So if you try this in your calculator, try 3 divided by 1 million. That number is going to be very, 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 very small. Now try 3 over, 1 gazillion, right? That's going to be almost 0, right? So the idea here is that if you have a real number divided by a huge number, by infinity, and then that's going to be 0, right? So, and then similar properties hold for the one-sided limits for any of these functions. And also, it also holds for the negative infinity approach. All right, so here we have a few examples. Because the limit of, let's say we have a limit of 1. Well, we know the limit of 1 is 1, right? So that's given to us. The limit of 1 over x squared, well, this is becoming, this is going to be infinity. So we can conclude that if we're adding a constant plus infinity, then that should give us infinity, right? What about the next one? We're approaching the function as x approaches 1 from the left. That's going to give us 2, and they're giving us that this is approaching negative infinity. So if you have the top, which is 2, and the bottom, which is negative infinity, well, what happens is you have a constant over a huge number, right? And it doesn't matter actually if it's negative, the huge number, right? This negative infinity, it's still nonetheless still going to be 0, right? So if you have a constant over infinity or a constant over negative infinity, either way it is going to be a 0, just like over here, right? Like over here. And this holds also if this would have been negative infinity. Okay, so let's say we have the limit of 3, which is 3, and the limit of cotangent of 0 goes from the right side is infinity. So if we multiply those two together, we have a constant times infinity, we go to infinity, right? So again, this is a very informal way to think about it, and sort of kind of help us sort of make the right conclusion. But we got to be careful, because if you have, let's say, infinity over infinity, then that's something we need to stop and think about. Or we have 0 over 0, then that's something we have to actually worry, do something different. So in the next example, we have x. The limit of x squared as x goes to 0 from the left side is 0, and the limit of 1 over x as x goes to 0 from the left side is negative infinity. If we are adding those two items, we have 0 sort of added to negative infinity. Well, nothing added to negative infinity. Negative infinity will overpower any real number, so therefore the end result will be negative infinity. All right, so what we're saying here is focus on the vertical asymptotes, recognize how you can do the vertical asymptotes, which is mainly looking at the bottom, making sure the numerator is not a 0, knowing that we now know that infinity is an expression that we use when the function is increasing without bound or decreasing without bound. Nonetheless, we can still think about it as we can plug in, we sort of plug in those numbers into the function, right, and use them as sort of algebraically. We can sort of algebraically multiply by infinity. We can algebraically divide by and you guys can't tell, but I'm actually putting quotation marks in my expression. Obviously you can't see it, so I gotta make sure I say that, because that's very informal, right? It's very informal. So, but it works. It works. All right. So I hope this is helpful. Let me know if you have questions. I'll see you guys in class.